Hey guys, welcome back to chapter 15. In this video, I'm going to walk you through another perfect square example. So now we have multiple ways to solve these really hard equilibrium problems. You could use the quadratic formula method. This method works all the time. It doesn't matter what kind of problem it is. So if the quadratic formula method works for you and you like it, you can continue to use it. The first simplification that I've showed you is the perfect square, and that's what this video is going to address, is it's going to show you another example of the perfect square. Okay, so here's our reaction. Why don't you guys go ahead and pause the video and get as far into it as you can, then I'll catch up with you on the other side. All right, so for this reaction, the flask initially contains 0.8 of our P4 and 0.84 of our O2. What will the concentration of the product be at equilibrium? All right, so we're going to set up our ice table. Initial, change, equilibrium. We're going to put in each of our chemicals, so P4, O2, and then our product. And again, we're going to use that little hint where we put that coefficient here so we don't forget it. All right. So initially it contains 0.84 of both of our reactants, no initial mention of our products. So we're going to assume that that's 0. The change, our products are going to have to go up by a factor of 2x. So they're going to go up by a factor of x, and then we multiply it by 2 because of that coefficient. Our reactants are going to go down by a factor of x and down by a factor of x. So at equilibrium, these are 0.84 minus x, 0.84 minus x, and 2x. All right, now our equation for K. So K equals concentration of our products over the concentration of our reactants. And plug in what we know. 8.4 times 10 to the negative 5th equals, on the top, we're going to have 2x squared. On the bottom, we're going to have 0.84 minus x, 0.84 minus x. So if you see something that looks like this, you should automatically throw your hands in the air and say, hallelujah, she gave me a perfect square. Remember, I can simplify this on the bottom as such. Okay, so this should be good news for you. I gave you a simple one. So we're going to take the square root of both sides. Let me clean up the right-hand side first because that's a little bit easier. So this is going to leave us with 2x over 0.84 minus x. So this is the inverse. It essentially cancels these out. And then for the right-hand side, I just need to plug that into my calculator because it's a regular old number. So square root of 8.4 times 10 to the negative 5th gives me 0.009. From here, it's a pretty easy algebraic rearrangement. So let me just recopy this where I have more room. So 0.009 equals 2x over 0.84 minus x. So first thing I'm going to do is get this out of the denominator, so out of the bottom. So that cancels. Whatever I do to the right side, I have to do to the left side. Okay. So then distribute this through. So 0.84 times 0.009 equals 0.00756 minus 0.009x, and we're left with 2x on this side. And then again, I want to get all my x's on the same side, so I'm going to multiply, or excuse me, I'm going to add by the 0.09, so those cancel. add by the 0.009. And I have 0.00756 equals 2.009x. And then we want to get x by itself. So x equals 0.00756 divided by 2.009. And x equals 0.0038. So it's not asking for x, it's asking for the concentration of PO2 at equilibrium. So going back to our ice table, this is the concentration of the P2O at equilibrium. So 2 times x would be that concentration. So the concentration of P2O equals 2 times the 0.0038. So concentration of PO2 equals 0.0038 times 2 equals 0.0076 molar. So that's the answer you would type in. So another example of the perfect square. I hope you guys found this helpful.